Hey everyone, this is a video to summarize the calculations behind dealing with reactions and molarity. You can also think of this as what do you do when you're having to deal with the concentration of solutions that are present in a chemical reaction. So the previous two videos on solution concentration have only dealt with making a solution of a single substance, and now we're going to see what happens when those substances react with one another. So the best way to do this is to look at a practice problem. So consider the reaction 3 sodium hydroxide plus phosphoric acid yields 3 waters and sodium phosphate, and the reaction's been given and it's been balanced for us. How many milliliters of 0.5 molar NaOH are necessary to completely react with 17 milliliters of 1.5 molar phosphoric acid? I find it best to take the data that's provided to us and organize it, and I like to do that under the reaction equation. So we're told we have 0.50 molar sodium hydroxide, and it's going to react with 17 mils of 1.5 molar phosphoric acid. So we've got 17.0 milliliters of that. And what we're looking for is how many milliliters of the sodium hydroxide. So I'm going to put a question mark and milliliters there to remind myself that we don't know how many milliliters, we don't know the volume of the NaOH, and we're asked for that in the units of milliliters. So that's what we're solving for. So the way you're going to do this is never start with the concentrations, because it turns out we're going to use those as conversion factors. We're always going to start with the volume of the thing we know most about, which in this case is the phosphoric acid. So we know the concentration, we know the volume. We're going to start with that volume. And what we're going to do is we're going to change that volume from milliliters to liters. And then we're going to treat this molarity as a conversion factor. What do I mean by that? So when you see 1.5 molar, that's the same as 1.5 moles of, in this case, phosphoric acid in a liter of phosphoric acid solution. That's what, so this capital M is doing a lot of work, as they say, because that capital M is actually telling us that this is kind of a hidden unit. It's kind of like miles per hour. When we write out miles per hour, we tend to write mph. What that really means is the number of miles you go in an hour. So molarity is the same way. It's how many moles of a substance are there in a liter of that solution, all right? And because we can write this as a fraction, that means we can use it as a conversion factor when we're doing conversions. So now we're in a milliliter. Oh, and I'm being sloppy and not writing my substances down here. So this is a milliliter of phosphoric acid. This is a liter. So now we can say, all right, for every 1 liter of phosphoric acid, we know that 1.5 moles of H3PO4 are present. All right. Again, this is just another way of writing that molarity value that we were given. Okay. All right. So now we're in moles, and now we're kind of off to the races because we know next thing to do is a mole-to-mole ratio. And from our reaction equation, we have that 1 mole of H3PO4 is going to react with 3 moles of sodium hydroxide. Remember, we're trying to get to the milliliters of sodium hydroxide here. So that's where we're going. And now we got to get from moles to volume. Well, how do we do that? Well, we're going to do the same trick we did just a second ago, except now we're going to use the molarity of the sodium hydroxide. So there's 0.500 moles of NaOH in a liter of sodium hydroxide solution. Okay? I know it looks weird because it feels upside down to people, but it doesn't matter because it's just a conversion factor. We can flip conversion factors all day, right? It's like you can have 100 centimeters over a meter or 1 meter over 100 centimeters. It doesn't matter, right? And then we got one more step here because we got to go back to milliliters. The nice thing here is that notice that the thousands cancel because you've got one in the numerator, one in the denominator. You don't have to actually punch that in. So we're now grab our calculator, 17 times 1.5 times, that's it, divided by 1.5. Yeah, that's it. That's the only thing in the denominator. It's not a 1. And that comes out to be 51.0. Actually, it's 51 because this is the one time we have to look at the conversion factors. That's an experimental value. the molarity of the phosphoric acid is an experimental value, so it's only got 2 significant digits. So we're going to call that 51 milliliters of the NaOH is going to be needed. And that kind of makes sense. Although, no, it doesn't, because the phosphoric acid is 3 times the concentration, and we've got, oh, you know what? I didn't multiply my 3 here. So I'm going to go back and do that. Hold up. This is why you always check your answers. As I hope it's clear from these videos, if you don't check your answers, you're going to mess up on a regular basis, especially when you're talking through things and trying to explain it to people. All right, now we have a much better number. That's 153. That makes way more sense. Milliliters of NaOH. Okay, so I knew it had to be a big number because the phosphoric acid is 3 times as concentrated, and it takes 3 times as many formula units of sodium hydroxide as we have molecules of phosphoric acid. So, okay, so that's our answer. The big new concept here is this trick of using the molarity as a conversion factor. Okay, and you can do this, and it's totally fine, and it'll make your life a lot easier. Otherwise, you have to use the molarity equation twice, and you have to do a mole-to-mole ratio in the middle, and it becomes this big mess, and you don't want to deal with it. Okay? All right. We're going to do a practice problem here now. So as always, go ahead and pause the video at this point. Try to do the practice problem on your own on a separate sheet of paper, and then restart the video, and I'll go through the solution. One thing I'll mention first is that this is a little different in that we have a solid reacting with a solution. So you're only going to need the molarity once in the process as a conversion factor. All right, pause the video and give it a try. All right, hope you've had a chance to work through this now. So I'm going to do the same thing I did earlier, which is I'm going to organize my data. And I'm going to change my pencil color. There we go. So I have 1.57 grams, 1.75 grams of aluminum, and I have 0.90 molar copper chloride, but I don't know what volume of that. So that's where I'm going. So I know the most about the aluminum. That's where I'm going to start, and I've got 1.75 grams and of aluminum. And as always, when we have grams, the first thing we do is change grams to moles. Hopefully that's becoming a little bit of muscle memory for you, where you don't have to think through, oh my gosh, what I do. If you're given grams, go to moles. All right. Now we're going to do a mole-to-mole ratio because we know for every 2 moles of aluminum, we have 3 moles of copper chloride. Notice we know that from the balanced reaction equation. You should also just get the habit of double checking to make sure that the reaction equation that's provided to you is balanced. All right, now here, this is where we're going to need the molarity because we know that 0.9 molar means 0.9 moles of copper chloride per 1 liter of copper chloride solution. So we're going to flip that over, 0.9 moles copper chloride. And I'm going to show you a shortcut here. You can put 1,000 milliliters in the numerator here because 1,000 mils is 1 liter. So we can jump through that and save ourselves an extra step. So notice that grams of aluminum cancel, moles of aluminum cancel, moles of copper chloride cancel. We're left with milliliters of copper chloride. Hooray! So now 1.75 times 3 times 1,000 divided by, in parentheses, 26.98 times 2. That gives us 97. What do we got in terms of sig figs here? The molarity of the copper chloride limits us to 2. So we're going to call it 97 milliliters of that 0.9 molar copper chloride solution. That kind of makes sense. You tend to need a lot of solution volume unless it's really concentrated to use up solid. So I think we're going to call that one good. So again, we took our information, we put it down here to organize it. We started with the thing we knew the most about, which is the 1.75 grams of aluminum. Go from grams to moles, mole-to-mole ratio from the reaction equation, all of which you've known how to do. And the only new step here is using that molarity as a conversion factor. Try to get comfortable with using the molarity. Please don't ever write 0.9 capital M going to 1 thousand milliliters, like that drives me absolutely up the wall because that's like molars per milliliter and it makes no sense. It's not what you mean. Capital M does not stand for moles, it stands for moles per liter. So you actually need to write the word mole out here. If you want the abbreviation, it's MOL. I think that's silly. I always write MOLE out. Okay? All right. If you have any questions, please leave them in the comments or get in touch. And